mat also prevents the vertical motion of the electrolyte within the battery. When a normal wet cell is stored in a discharged state, the heavier acid molecules tend to settle to the bottom of the battery, causing the electrolyte to stratify. When the battery is then used, the majority of the current flows only in this area and the bottom of the plates tends to wear out rapidly. This is one of the reasons a conventional car battery can be ruined by leaving it stored for a long period and then used and recharged. The mat significantly prevents this stratification, eliminating the need to periodically shake the batteries, boil them, or run an equalization charge through them to mix the electrolyte. Stratification also causes the upper layers of the battery to become almost completely water, which can freeze in cold weather. AGMs are significantly less susceptible to damage due to low temperature use. While AGM cells do not permit watering, typically it is impossible to add water without drilling a hole in the battery. The recombination process is fundamentally limited by the usual chemical processes. Hydrogen gas will even diffuse right through the plastic case itself. Some have found that it is profitable to add water to an AGM battery, but this must be done slowly to allow for the water to mix via diffusion throughout the battery. When a lead-acid battery loses water, its acid concentration increases, increasing the corrosion rate of the plates significantly. AGM cells already have a high acid content in an attempt to lower the water loss rate and increase standby voltage, and this brings about shorter life compared to a lead-antimony flooded battery. If the open circuit voltage of AGM cells is significantly higher than 2.093 volts or 12.56 V for a 12V battery, then it has a higher acid content than a flooded cell. While this is normal for an AGM battery, it is not desirable for long life. AGM cells that are intentionally or accidentally overcharged will show a higher open circuit voltage according to the water lost and acid concentration increased. 1 amp-hour of overcharge will electrolyze 0.335 grams of water per cell. Some of this liberated hydrogen and oxygen will recombine, but not all of it. Gelled electrolytes. During the 1970s, researchers developed the sealed version or gel battery, which mixes a silica gelling agent into the electrolyte. Silica gel-based lead-acid batteries used in portable radios from the early 1930s were not fully sealed. This converts the formerly liquid interior of the cells into a semi-stiff paste, providing many of the same advantages of the AGM. Such designs are even less susceptible to evaporation and are often used in situations where little or no periodic maintenance is possible. Gel cells also have lower freezing and higher boiling points than the liquid electrolytes used in conventional wet cells and AGMs, which makes them suitable for use in extreme conditions. The only downside to the gel design is that the gel prevents rapid motion of the ions in the electrolyte, which reduces carrier mobility and thus surge current capability. For this reason, gel cells are most commonly found in energy storage applications like off-grid systems. Maintenance-free, sealed, and VRLA, valve-regulated lead acid. Both gel and AGM designs are sealed, do not require watering, can be used in any orientation, and usable for gas blow-off. For this reason, both designs can be called maintenance-free, sealed and VRLA. However, it is quite common to find resources stating that these terms refer to one or another of VC designs, specifically. In a valve-regulated lead acid, VRLA, battery, the hydrogen and oxygen produced in the cells largely combine into water. Leakage is minimal, although some electrolyte still escapes if the recombination cannot keep up with gas evolution. Since VRLA batteries do not require, and make impossible, regular checking of the electrolyte level, they have been called maintenance-free batteries. However, this is somewhat of a misnomer. VRLA cells do require maintenance. As electrolyte is lost, VRLA cells dry out. and lose capacity. This can be detected by taking regular internal resistance, conductance, or impedance measurements. Regular testing reveals whether more involved testing and maintenance is required. Recent maintenance procedures have been developed allowing rehydration, often restoring significant amounts of lost capacity. VRLA types became popular on motorcycles around 1983-23, because the acid electrolyte is absorbed in TOF separator, so it cannot spill. 24. The separator also helps them better withstand vibration. They are also popular in stationary applications such as telecommunications sites, due to their small footprint and installation flexibility. 25. Applications. Most of the world's lead-acid batteries are automobile starting, lighting, and ignition (SLI) batteries, with an estimated 320 million units shipped in 1999. 8. In 1992 about 3 million tons of lead were used in the manufacture of batteries. Wet cell standby, stationary batteries designed for deep discharge are commonly used in large backup power supplies for telephone and computer centers, grid energy storage, and off-grid household electric power systems. 26. Lead-acid batteries are used in emergency lighting and to power sump pumps in case of power failure. Traction, propulsion batteries are used in golf carts and other battery electric vehicles. Large lead-acid batteries are also used to power the electric motors in diesel-electric, conventional submarines when submerged, and are used as emergency power on nuclear submarines as well. Valve-regulated lead-acid batteries cannot spill their electrolyte. They are used in backup power supplies for alarm and smaller computer systems, particularly in uninterruptible power supplies, UPS, and for electric scooters, electric wheelchairs, electrified bicycles, marine applications, battery electric vehicles or micro-hybrid vehicles, and motorcycles. Many electric forklifts use lead-acid batteries, where the weight is used as part of the counterweight. Lead-acid batteries were used to supply the filament, heater, voltage, with 2V common in early vacuum tube, valve, radio receivers. Portable batteries for miners' cap lamps. Headlamps typically have 2 or 3 cells. 27. Cycles. Starting batteries. Lead-acid batteries designed for starting automotive engines are not designed for deep discharge. They have a large number of thin plates designed for maximum surface area, and therefore maximum current output, which can easily be damaged by deep discharge. Repeated deep discharges will result in capacityless and ultimately in premature failure, as the electrodes disintegrate due to mechanical stresses that arise from cycling. Starting batteries kept on a continuous float charge will suffer corrosion of the electrodes, which will also result in premature failure. Starting batteries should therefore be kept open circuit but charged regularly, at least once every 2 weeks, to prevent sulfation. Starting batteries are of lighter weight than deep cycle batteries of the same size, because the thinner and lighter cell plates do not extend all the way to the bottom of the battery case. This allows loose disintegrated material to fall off the plates and collect at the bottom of the cell, prolonging the service life of the battery. If this loose debris rises enough, it may touch the bottom of the plates and cause failure of a cell, resulting in loss of battery voltage and capacity. Deep cycle batteries. Specially designed deep cycle cells are much less susceptible to degradation due to cycling, and are required for applications where the batteries are regularly discharged, such as photovoltaic systems, electric vehicles, forklift, golf cart, electric cars, and others, and uninterruptible power supplies. These batteries are shaved thicker plates that can deliver less peak current, but can withstand frequent discharging. 28. Some batteries are designed as a compromise between starter, high current, and deep cycle. They are able to be discharged to a greater degree than automotive batteries, but less so than deep cycle batteries. They may be referred to as marine forward/motorhome batteries, or leisure batteries. Fast and slow charge and discharge. Charge current needs to match the ability of the battery to absorb the energy. Using too large a charge current on a small battery can lead to boiling and venting of the electrolyte. In this image, a VRLA battery case has ballooned due to the high gas pressure developed during overcharge. The capacity of a lead-acid battery is not a fixed quantity but varies according to how quickly it is discharged. The empirical relationship between discharge rate and capacity is known as Burkert's law. When a battery is charged or discharged, only the reacting chemicals, which are at the interface between the electrodes and the electrolyte, are initially affected. With time, the charge stored in the chemicals at the interface, often called interface charge or surface charge, spreads by diffusion of these chemicals throughout the volume of the active material. Consider a battery that has been completely discharged, such as occurs when leaving the car lights on overnight, a current draw of about 6 amps. If it then is given a fast charge for only a few minutes, the battery plates charge only near the interface between the plates and the electrolyte. In this case, the battery voltage might rise to a value near that of the charger voltage. This causes the charging current to decrease significantly. After a few hours, the interface charge will spread to the volume of the electrode and electrolyte. This leads to an interface charge so low that it may be insufficient to start the car. 29. As long as charging voltage stays below the gassing voltage, about 14.4 volts in a normal lead-acid battery, battery damage is unlikely, and in time the battery should return to a nominally charged state. Sulfation and desulfation. Lead-acid batteries lose the ability to accept a charge when discharged for too long due to sulfation, the crystallization of lead sulfate. 30. They generate electricity through a double sulfate chemical reaction. Lead and lead dioxide, the active materials on the battery's plates, react with sulfuric acid in the electrolyte to form lead sulfate. The lead sulfate first forms in a finely divided, amorphous state and easily reverts to lead dioxide, and sulfuric acid when the battery recharges. As batteries cycle through numerous discharges, sulfated plates from a 12V5 are battery and charges. Some lead sulfate does not recombine into electrolyte and slowly converts into a stable crystalline form that no longer dissolves on recharging. Thus, not all the lead is returned to the battery plates, and the amount of usable active material necessary for electricity generation declines over time. Sulfation occurs in lead-acid batteries when they are subjected to insufficient charging during normal operation. It impedes recharging. Sulfate deposits ultimately expand, cracking the plates and destroying the battery. Eventually, so much of the battery plate area is unable to supply current that the battery capacity is greatly reduced. In addition, the sulfate portion of the lead sulfate is not returned to the electrolyte as sulfuric acid. It is believed that large crystals physically block the electrolyte from entering the pores of the plates. A white coating on the plates may be visible in batteries with clear cases or after dismantling the battery. Batteries that are sulfated show a high internal resistance and can deliver only a small fraction of normal discharge current. Sulfation also affects the charging cycle, resulting in longer charging times, less efficient and incomplete charging, and higher battery temperatures. SLI batteries, starting, lighting, ignition, For example, car batteries suffer the most deterioration because vehicles normally stand unused for relatively long periods of time. Deep cycle and motive power batteries are subjected to regular controlled overcharging, eventually failing due to corrosion of the positive plate grids rather than sulfation. Sulfation can be avoided if the battery is fully